So, welcome to our discussion on instrumental variable estimation technique. And yesterday we were talking about we were discussing how to detect endogeneity in a model before we actually implement instrumental variable estimation. And the test what we are discussing was the Haussmann test, which is also known as Darwin-Wu-Haussmann test, because the test was developed by these three econometricians, Darwin, Wu and Haussmann. So, quickly we will recap what we are doing in this test. Basically, let us say y1 equals to beta 0 plus beta 1 y2 plus beta 2 z1 plus u1. Y2 is the endogenous variable and this is Z2, which is instrument that we are using. So, basically what we are doing, we were running a reduced form equation y2 equals to pi 0 plus pi 1 z1 plus pi 2 z2 plus v2. So, we are trying to get this is y2 hat and this is v2 hat, and what we are doing, we are estimating the predicted value of the error term from this reduced form equation, and we are putting the predicted value of the error term in the equation as an additional explanatory variable, and then we are checking whether the coefficient of that predicted error term is significant or not. If significant, then we say that there is endogeneity. If not, then we will say that there is no endogeneity. So, that is the mechanism we discussed. So, once again we will use the same data set, we will see. So, this is our data set, and what we will do, we will first regress education on experience, let us say experience, and father's education or and mother's education. So, this is the model, this is the reduced form equation for education. We are regressing on the excluded exogenous variables father's education and mother's education, and included exogenous variable is experience. Then predict let us say V residual, and then variable V already defined. Okay, then what we will do, we will take predict some different name, predict U1 residual. Okay. So, then we will regress what we will do, regress log wage on education, experience and this predicted error term. And if we look at the coefficient of this predicted error term, the t value is 1.60 and the p value is 0.10. So, that means this is not significant. This is not significant, right. So, that means what would be our conclusion, that education is actually not an endogenous variable in this particular context. Okay. Now, the manual detection of instrumental variable estimation technique, we can actually do by this using the the status command. In that case, what we have to do, we have to first estimate the equation using IVReg LOH, then we will put education equals to father's education, mother's education, and then we have experience. So, this is the model. After this, what we have to do, E stat endogenous. That is what we discussed, E stat endogenous. So, what we will do, will so this is our model ivrig LOH. Then the command what we are using, E stat endogenous. Okay, yesterday it was working. What is the problem of this command? E stat endogenous. Okay, we'll use instead of this IV regress IV regress to SLS. Okay. Okay. So, instead of IV reg, we have used IV regress to SLS, and then this is stat endogenous command is working. Now, what we have to take this Wu-Hussmann statistic, which is the F value, and corresponding T statistic is 2.46, right. Now, this F value, this this Wu-Hussmann test statistic is basically, the F value is nothing but, if we go back, then it is actually the square root of this T value. Okay. So, that means when we are doing it manually, we are using T statistic to test the individual significance of the predicted value of the error term, right. And when we are using, when you are using this Durbin-Wu-Hussmann test, that is the F statistic we are using, where the value of this F is nothing but this square root of the previous T value, okay, right. Now, what exactly we are doing here in this Durbin-Wu-Hussmann test, that is something we need to discuss, right. Now, in Durbin-Wu-Hussmann test, what they suggest basically, if you recall, what is the philosophy of Hussmann test? We need to estimate the model using OLS, we need to estimate the model using IV, and then we need to check whether the coefficients, estimated value of the coefficients derived from the OLS and that from the IV, they are statistically different or not. If there is a significant difference in between OLS and IV estimates, then we will say that OLS is actually not an appropriate method of estimation, right. Okay. So, let us say that the same model, this model we are using first OLS. Okay. Our null hypothesis is OLS is actually a valid estimation method. Okay. That is the null hypothesis. And what is the alternative? Alternative hypothesis is that IV is valid estimation. Let us assume that beta hat this is C, that means consistent estimate of this beta 1 hat, what we are doing. Okay, let us say this is the endogenous variable. So, beta 1 hat which is consistent, okay, under both H naught and H A. So, what we know that if OLS is actually a valid estimation technique, that means if there is no endogeneity in the model, then whether we apply OLS or IV, both the estimates would be consistent. So, there won't be any problem in consistency. So, beta hat C, that means is consistent under both H naught and H A, right, and beta hat E, the efficiency property, okay, efficiency property is efficient under H naught, but not consistent when the null is not true. Okay. So, that means if OLS is actually not valid, if there is endogeneity and if we still apply OLS, then the resultant estimates won't be consistent. Okay. That is the problem of applying OLS. When there is endogeneity, we will lose consistency, will lose the consistency property. Okay. All right. So, once again what I repeat that in presence of OLS, if there is no endogeneity, whatever we apply, whether it is IV or OLS, both the estimates would be consistent. Okay. Consistency would be preserved. But if there is no endogeneity and if we still apply IV, then the efficiency property to some extent we have to sacrifice, because IV estimates standard error are larger than the OLS standard error. And beta hat E, which is actually efficient estimator, that means it is fully efficient under H naught, that means when there is OLS, if we apply OLS, fully efficient when there is no endogeneity, but it is not consistent when H naught is true, that means when there is endogeneity, this beta hat E is actually not consistent. So, that is why the test statistic is constructed in Wu-Hofmann test. This is Darwin Wu-Hofmann test. Test we are talking about. So, it is beta hat C minus beta hat E transpose, these are all in vector form, variance of beta hat C minus variance of beta hat E inverse beta hat C minus beta hat E, that is the Darwin-Uhosman test, or in short DWH. And this follows a chi-square distribution with degrees of freedom equals to number of endogenous variable. In this case, we have only one endogenous variable, that is why it is 1 here. So, this will follow a chi-square distribution. So, this test, this Darwin-Uhosman test is basically a chi-square test. So, that means here in this output we have one Darwin score, okay, Darwin score, and that Darwin score is actually coming from here, because this is a chi-square distribution, and if you look at this is also a chi-square distribution. But other Hosman test, what we manually did, that is basically an F test, which is basically the square root of this t, okay, right. So, Stata is reporting Darwin chi-square score as the Darwin-Uhosman test, right, okay. So, this test can also be implemented additionally. What they say, so that means we can say that this test is more of a test for whether OLS is valid or not, rather than testing endogeneity, okay. So, the entire philosophy of Hosman test is based on two alternative methods of estimating the same equation, one by OLS, another by IV, and then we test whether there is significant difference between the beta hat OLS and IV, because here we are writing beta hat C and beta hat E. C is consistent, E is efficient. Consistency is preserved under IV and this is under OLS. So, this is IV minus OLS. Again this is variance of beta hat IV minus OLS. Again this is IV minus OLS. So, the entire DWH test statistic is based on how far the IV estimates are different from the OLS estimates. That is the philosophy, that is the logic of Hosman test. So, this logic also we can implement using Stata command, and we will now see how to do it. So, we will say that let us say IV reg LOH, then education equals to father's education, mother's education, then experience. So, we are estimating the model using IV, then we will store this result EST store IV, okay. Then we will use the same equation, estimate the same equation using OLS. So, using reg command, reg LOH education experience, okay. Then what we will do, we will put Hosman IV and the command is constant sigma mod. This is the command. So, we will first estimate the model using, so this is what is working here. So, what I am saying, we will first estimate the model using IV, okay, that means 2SLS method, then we will use the same equation by OLS, and then by putting this command Hosman IV constant sigma mod, we are actually asking Stata to report the DWH test statistic. How is it doing? Look at here. B, that means these IV estimates are consistent under H naught. So, what is H naught? OLS is appropriate, okay. when is OLS appropriate? There is no endogeneity. So, when there is no endogeneity, IV is consistent, OLS is also consistent, but this B is actually inconsistent under HA. So, that means when there is endogeneity and if we apply OLS, then that would be inconsistent. Okay. So, in our result, this beta hat C and beta hat E, stata is denoting as B and capital B, and then they are taking this, and ultimately they are arriving at this chi-square value, which is 2.46, right. And if we look at the istat endogenous, look at the same thing, 2.46. Okay. So, chi-square is 2.46. So, almost this chi-square, sorry, this is the F test, this is 2.47. So, almost same value we are getting at. So, this is a chi-square test statistic, that means whatever we are getting here and the same thing stata is reporting here in this chi-square, alright. So, this particular test is based on Darwin's Wu-Hossmann test. This is the stata command, right, stata command, and test statistic once again this is the test command. Test statistic beta hat C minus beta hat E, variance of this, right. Okay. So, either we can do it manually, or manually generally we do not do it, we will simply use this istat endogenous command. Where is the istat endogenous? If you look at, this is the command, istat endogenous, okay, istat endogenous. So, this is how we have to test for endogeneity, but this test, as I said, it has a limitation. For example, what is the limitation we said? When there is more than one endogenous variable, it will only say whether there is endogeneity or not, but it cannot say, it cannot detect which particular variable is endogenous. So, for that I will give you an example. So, IV reg L wage, then education equal education, and let us say we have experience also as another endogenous variable, equals to right. And then if we put, oh sorry, this IV regress we have to use, otherwise it will not work. So, IV regress to SLS. So, whenever we are using this command, we have to use IV regress to SLS, otherwise istat endogenous will not work. IV regress to SLS. And then istat endogenous will work. Okay. Now, if you look at what is the null hypothesis here, variables are exogenous and we cannot reject the null also. So, there is no endogeneity problem, but the difficulty is here they are saying all variables are exogenous, but which particular variable is exogenous, whether one variable is exogenous or all the variables are exogenous, that we cannot say, because it is based on an F statistic which is saying that whether the variables are significant jointly or not. When there are two endogenous variables, we will get two reduced form equation. From the two reduced form equation, we will get two predicted value of the error term, let us say V1 hat and V2 hat, and these two predicted value of the error terms we will put it in the structural equation, and then we will implement one F test to test whether V1 hat and V2 hat they are jointly significant. And what is the alternative of this F test? At least one among them is significant, right. So, if it is at least one, then I do not know whether that education is endogenous or experience is endogenous or both of them are endogenous. That is the limitation of this test. To overcome this, what we have to do? We have to use another command we have to keep in mind. Oh, here again we have to use IVReg. So, instead of this, IVReg LOH and then IVNdog. Okay, we have to install this command. Okay, so we have to install this command. Oh, which we cannot, since this is not connected, I think we cannot install also. Anyway, after estimating this model, if you put IVNdog, then here if I put IVNdog and you have to put which particular variable to use for endogeneity. We have two endogenous variable. So, after IVNdog, if you put education, then that should work. Here I am not able to use this IVNdog because this command I am not able to download here since it is not connected. Okay. So, here I am not able to connect this. Okay, SSC install IVNdog. So, if it does not work, nothing to be worried. So, what I am saying, using this IVNdog command, you can specify which particular variable you want to use for endogeneity. So, you can first use IVNdog education and see whether education is endogenous or not. Then after that, you can use IVNdog experience to test whether experience is endogenous or not. So, this way you can actually test the endogeneity of a specific variable, which was the limitation of the Hofmann test, since Hofmann test uses the F test. That is the problem.